Okay guys, sorry. I was trying to do the last video on the Lewis structures, but I was cut off in doing IF5 the previous time, and there were some other molecules a cast of miscellaneous molecules that I also wanted to do, just to make sure that we cover as many molecules as we could. So I'm going to continue this and on a very short video, trying to wrap up any hyperactivated cases and then some other molecules and some strange cases as well. So let's just go back. We were cut off here trying to do I5, and it was an octahedral framework that has one lone pairs on octahedral goes top or down axial. So if we just detach the one on the top here, we could also do this. That doesn't really change anything. It could give me a square pyramidal. We could also show this, that a square pyramidal is just like this. We don't have to do this, but just for one time so that you could see how a square pyramidal, what does that square pyramidal really means. There's a square on the top and then the pyramidal thing that is the pyramidal aspect of it. If I just get rid of this iodine in the center and put boramine instead, I'm not going to start from scratch. That gives you the BRF5 as well. Let's just do I5 plus and IF4 plus as well. So I5 plus, this is going to be the last example of hyperactivation. I plus is just group 6, following group 7, if it's, or iodine is also group 7, going to plus I plus, that is going to resemble a structure, the configuration of group 6 oxygen. So I could shave in a friendly manner without attacking anyone's lone pairs with two fold-rings, my two single reacting electrons on I plus, and it will satisfy not only the I plus but also the surrounding fold-rings. And we have, oh, not bad. Let's try to do iodines here because I'm doing I5 plus first. So it would not only satisfy the surrounding iodines but also the central I plus iodine, and then there are two more. Okay, and iodine is not going to do anything because it fills octet. Okay, so what I'm going to do, I'm going to rip off this, shatter this lone pair to hoisting the two other iodines. That's I5 plus, one lone pair, four surrounding atoms, 5 a trigonal bipyramidal geometry. Let's get into this. The trigonal bipyramidal geometry, if I take care of the lone pair, any of these, now I do this one to give me a seesaw molecule. Okay, a seesaw geometry. I could also draw the seesaw real quick here. I first do the plane, in plane position. In the center, I'll put my iodine. The charge should go for the whole molecule. And then the lone pair, it's preferable to put it here rather than here. And here, it's not going to be wrong. It just gave you a better representation of something that is like a seesaw. I. This is I5 plus, and with the seesaw geometry, just like this. And I could also replace all the four surrounding iodines with fold-rings to give you the exact same structure of IF4 plus. I'm not going to do it from scratch because that would give up. I would end up having the same exact geometry, the seesaw geometry. Now, let's move on real quick to two examples, to my miscellaneous examples. N3 minus, we remembered we didn't do this, and NO plus. NO plus is just a, NO plus is just the linear molecule. N plus is just like carbon, and O is group 6. So I could do a double bond. This is my N plus, by the way. To do this, it will satisfy my oxygen, but it won't satisfy my carbon-like configuration, the N plus. Okay, it needs two more, just like a carbon. A carbon needs 4 bonds to be satisfied. My N plus here have 2. It needs 2 more, so I'm going to donate this with pairing up this to open up a space. Okay, so that's NO plus. That is like just the structure of CO, the carbon monoxide. If you go back to I believe our first video. Okay, that's NO plus, a linear molecule. And N3 minus, we're going to start with this, and we have an N minus. So this is an exception here we took n minus outside. We could also do it with n minus in the center, but it's preferable to do it like this because the central atoms are the ones that has the maximum number of single reacting electrons, and that are the two nitrogens that each have 3. Okay, and then you donate this to actually satisfy the hunger of n minus, which is exactly like an oxygen. Okay, so it can accept a Div bond. Okay, so that's what you do. And here what I want to do as well is to show you how could I do it if it's n minus in the center, just like oxygen. I could do this using a conception of just one single bond between this one and this one. It would satisfy my n negative in the center, but it won't satisfy my two surrounding nitrogens, so I'm going to donate. Each of them needs 2 more, so they're going to pair up their 2 single reacting electrons and each receive a Div bond from the central nitrogen. Both representations are correct and gives you linear geometry, but this one is the most correct one, okay? Because we start with the central atom that has maximum number of single reacting electrons. Let's move on to CH6, C2H4 real quick. Now these are more organic molecules, so I'm not going to do much about them. Hydrogen, hydrogen, also hydrogen, hydrogen here. So if I do this and this, and also this and this, you could see that, okay, I have my 2 carbons and each of them has 2 more single reacting electrons, which is with the double bond. That would mean each carbon has 3 surrounding atoms, no round pair, so it would be trigonal planar on both. Okay, this is just like the oxalate that we do, ethylene or C2H4. C2H6, that's benzene molecule that we talked about Auguste Kekulé in the first session. Let's just do it real quick. Let's do it in a smaller way so that I could show you how that works. Carbon, 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 carbon. So each carbon has 4 surrounding, 4 surrounding single reacting electrons. Each hydrogen has also 1. As I do connect each hydrogen reacting with one of my carbon single reacting electrons, each carbon now has 1, 2, 3. Okay, so I could do alternate single and double bonds to fulfill the desire of each of those carbons. This is the structure of benzene. Each carbon has 4 bonds, so it's satisfied 4, 4, 4, 4, all 4, and my hydrogens are also satisfied. Okay, that's benzene, and it's a planar molecule. BH3, remember we talked about BH3, those are the 2 ones that I may want to finish with, BH3 and BeCl2. BH3 boron is group 3. Okay, so it has 3 single reacting electrons, hydrogen, hydrogen, hydrogen. Each of them reacts with one of these single reacting electrons. You have no lone pair, 0 lone pair, 3 surrounding atoms. That gives you this kind of structure. Okay, but BH3 doesn't have boron to get the complete octet. Okay, that's why 2BH3, BH3 is sort of unstable. I told you about that. With boron and beryllium, you could have unstable structures. So the BH3, 2BH3 could join together to give you a structure that is like this. Now BH3 is like this, trigonal planar, but it could arrange itself to actually open up a space, another orbital. It is just like a tetrahedral that if I detach one of these elements, a BH3 going from this sort of trigonal planar to a pyramidal sort of geometry. Okay, with one of these places opened up as an orbital. This is the BH3 here. Now in this empty space, it could actually accept a company of a bond, okay? Now these two electrons are going to be shared between the 3 atoms. I'm going to draw them in blue so that you could see what happens. There would be a bond like this and a bond like this. We call them 2 electron 3 center bonds, okay? And it's just like if you attach 2 of these together, one BH3 like this, okay? This is the one that donates the hydrogen on the top, and this BH3 would also be this one with the hydrogen that is in the bottom, okay? And it's going to actually, the 2 are going to join together. But again, it has to go from this configuration to this configuration for those 2 BH3 to join together to give B2H6, okay? Now B2H6 have both borons being satisfied through octeteral, because you could see each of these 2 electron 3 center bonds, are going to contribute 2 electrons to boron, so 2, 4, 6, 8. Now that's how BH3 makes itself stable. Also BeCl2, it's going to be the same exact concept for that one. This is the structure. It's going to be linear. On the beryllium, you have 2 single reacting electrons that react with the 1 single reacting electron on each chlorine. And that's going to give you this structure, linear. But BeCl2 in reality is not stable. It's going to polymerize. So you would have 2 of those chlorines, just like I showed you for the structure of and it's going to continue towards other beryllium atoms, okay? So it's a beryllium over here and also a beryllium over here, okay? So that's how this whole thing works. N of these units, okay? This is a Be2Cl4 unit, and it's going to actually be a polymeric chain, and that's have those. Now all of these correctly represented should be these 2 2 electron 3 centers bonds, okay? All of those, also here, okay? That's BeCl2, which would polymerize. And let me see if I have any other molecule that we have not talked about and I'm interested to talk about. We do ethylene, we do benzene, we do these 2 molecules. I also want to do 2 examples of weird molecules, the phosphorus oxygen compounds, okay? That unlike other acids have hydrogens in hydroxyl group, these 2 molecules have hydrogens that are attached to phosphorus directly, okay? And that's what makes them weird, okay? And you have to know this, like someone have to tell you about the functionality, the acidic functionality of this. This is H3PO3 and H3PO2. Now we draw the H3PO4, the phosphoric acid, and that was the octahedral framework for that one. Okay, that's that one. H3PO4, we don't want to talk about it anymore. For H3PO3, there is 2 OH functionalities rather than 3. You have phosphorus is group 5, you have 2 OH functionalities. It is a diprotic acid, and the third one is going to be a third hydrogen directly attached. This is the weird feature in phosphoric acids, okay? This is phosphorus acid, and then the third oxygen is going to actually receive a native bond, okay? And that's the structure, a tetrahedral structure. Like that. Also for H3PO2, let me draw it here. It has only 1 OH functionality. That's a monoprotic acid. And the two other hydrogens are going to be just like this, fulfilling the phosphorus octet. And then there's one more oxygen because we have two oxygens and no choice of doing a day-leave bond. Okay, that also would give you a tetrahedral framework. This time, two of these hydrogens are going to weirdly attach to the phosphorus. We don't have this kind of feature, a hydrogen directly attached to a atom in any other acid other than the two weird phosphorus acid and hypophosphorus acid that we have. Okay, and I wanted to talk about these two as well. Again, we have covered many molecules. I'm gonna beg and actually ask you, if you're a student or professional, if you think of any other molecule that we have not drawn a Lewis structure for, please comment, add your molecule, and I'm going to talk about that in a separate video. Thank you for watching. We're posting other videos on chemistry as well, and this was our series for the Lewis structure, and I wish that if you follow this series of videos, you would be able to draw literally any molecule that you could see in any of these chemistry books or any other general chemistry book that you are studying in your high school chemistry or in your university or college chemistry, if you're doing general chemistry or basic chemistry. Thank you for watching, and let's wrap it up.